Okay, I wanted to talk a little bit about using some of the hardware available on the NetBurner board today. Next time we'll actually start talking about networking using the NetBurner board. But I wanted to talk about using some of the available pins to do I/O. Something you commonly want to do with microcontrollers, of course. And then we'll also talk about some of the interrupt support features and some of the timers that are available on the microcontroller. So most of this information is available actually in various application notes, which you can find on the NetBurner website. So these aren't included in the NetBurner documentation folder, which we've been using to find our documentation in the past, but I will make these available under today's lecture so that you can look at them if you wish. The NetBurner module actually brings out 100 pins from the processor. Okay, let's see if I can hold up the NetBurner board, the development kit here. The processor board actually has 100 pins on it and 250 pin connectors. And then we have access to all of those available pins on adjacent connectors that are just connected straight across. So these are the 100 pins I'm referring to. One of the connectors is labeled J1. That's actually the one that, as you're looking down at the development board from the top with the Ethernet controller at the top, J1 is the connector on the left, and J2 is the connector on the right. So like many microcontrollers, the signal pins have multiple functions, used for interrupts, UARTs, data, the data bus pins, address pins, I/O. 46 of the pins out of the 100 can be used for general purpose I/O. The GPIO pins are actually grouped into 8-bit ports, not if you take 8 times the 12 ports that are available, that's what actually 96 different pins. Only 46 of those are available for general purpose I/O though. So the ports have various names. The address port, the data high port, the data low port, UART ports, various, and so on. And this I think I took from one of the reference manual, shows some of the various multifunctions of the different ports. Now, in order to use the NetBurner board, you have to find out what the corresponding GPIO pin number is. So a couple things you can look at. One is, now this is in the NetBurner documentation directory. You go into the platform schematics, and it has a schematic of our development kit. So in the blue rectangle here shows the connectors that are under the processor board, and then it shows the two corresponding connectors that are on the development board, J1 and J2. And then you'll see a lot of the pins have various names like J25, J26. Most of these are actually general purpose I/O pins, and then so you can make connections to that corresponding pin, and then we can program that. Now these names are different than the names that are used on the microcontroller itself, so we have to find out this mapping between the pins on the schematic and then also the corresponding names that are used in the microcontroller documentation. I'll talk more about that in just a second. But the other thing that you have on here, if you scroll down in this schematic, you'll see which pins are actually connected to the LEDs and also the switches that are on the development board. And you'll notice here the anodes of the LEDs are tied high, so we need to take the corresponding port pin low to force current flow into the microcontroller to turn the LED on. And if we take, for example, J215 high, then that will turn LED 1 off. And similarly for the other LEDs. They're actually, for a couple of them, you have a choice of 2 different port pins that you can drive the LED with. For LED 3, it's connected to both J231 and J218. And then the dip switches, if you'll notice, they are also tied high on one side. Now you're going to be reading those. On the other side, they're connected via resistor to ground. So when the switch is on, this point will actually be high at 3 volts. When the switch is off, we've disconnected this line from the high supply and it's connected to a resistor to ground. So when the switch is off, we'll read a corresponding low signal. And you see the various dip switches, like dip switch 1 here is connected to J28. Now you can find the mapping between the connector designations, like J28, and the corresponding ports by looking in the various application notes. So this is the GPIO application note, and again this shows where was I looking at, J28. So it's connected to the P data high port, and P data high 15 is where J28 is connected. So again, looking back at this diagram, the port data high is actually where that pin is connected. The other way to do this mapping, so this application note talks about directly setting up the various ports using the control registers. And I'll talk a little bit about this, but this can be a little bit tedious and complex. There are a number of different control registers you have to set up properly. So again, I'll talk a little bit about that. But the other thing I want to talk about is there is a C++ pen class that you can use that makes that makes it easy to program these pens at a higher level without going through all the configuration directly of the control registers. That configuration of the control registers is actually hidden from you by using the C++ class. So this is documented in the PenIO application note. And again, here you'll find the mappings between the connectors and then the corresponding data pen function. You will want to refer to this when we use the pen class to get these specific definitions, because these are actually used when we use the PenIO class, and I'll show you that in just a minute as well. So going back to the lecture, okay, so I'll talk about configuring the control registers first, although once I show you how to use the PenIO class, you probably won't want to do this, but it does illustrate how you might want to, for your own microcontrollers, develop your own C++ class to access the pens at a higher level. Again, you have to know how to configure the control registers so you can actually write the underlying C++ code, but this makes it a lot easier for the application programmer to use. A lot of microcontrollers, I'm thinking of the Arduino, for example. They've used a number of C++ classes to make it really simple to program the microcontroller at a high level. But in the low-level approach, you have to configure the port correctly. That typically involves writing to the port assignment register to select the pen function, whether it's used for general purpose I/O or some other function. If it's used for I/O, you then have to configure the direction register, whether the GPIO pen is going to be used for input or output, and then you have to either set or clear the pen by writing to another register, or read a register if it's configured for input. So there are 12 sets of these registers corresponding to the 12 ports. Okay. So here's how you might configure J244 as an output GPIO pin and drive it high. So the code would look similar to this. And this requires looking into the microcontroller manual and finding out, whether these corresponding pins need to be set high or low. But here this is the port um, um, address register, where we're actually configuring it for general purpose I/O by writing a 1 into a particular spot, and we configure it for output by writing 1 to another control register, and then finally set the output um, to be this one is actually used to either connect it or disconnect it from a high impedance state by writing to another control register. Okay, so having gone through that, that's covered in more detail in that general purpose I/O application note, so you can find all the information there that you need to program at that level. But again, if you look at the Pen I/O application note, you'll see that the NetBurner provides a Pen I/O class, and it's defined in this header file, pens.h. So you have to include it, and then to set set a pen high, it's as simple as it's provided as an array for J2. So it's J2, the 44th element of the array. We have to set the function first to general purpose I/O. So this sets the function, and then you set that equal to 1 to drive it high. And so it's really easy then to set these pins high or low for when they're in the output state. You can set the functions of a lot of the pins on a pen by pen basis, whether it's general purpose I/O or has some other function. But the P-data pins, and there are 16 of them, and I think these are the ones that are all connected to the LED switches, the LEDs and switches on our development board. All use these ports. So these all have to be configured as general purpose I/O, or all of them have to have their other function. So just setting any one of the pins to general purpose I/O sets all of them to general purpose I/O. So that's done. We can do that quite simply with this command, setting the function. Earlier I showed setting a pen high just by setting it equal to 1. Alternatively, you can use the set and clear. Those are methods that are provided in the C++ class to set that pen high or to clear it. Alternatively, we can just set it equal to 1 or 0. If it's set for, we can use the read method if it's an input pin, and this will return a 1 or 0. So we could use the read method, for example, to read the state of our dip switches, and use set and clear to set the state, turn on and off the LEDs. Remember, a clear would actually turn on the LED because we have to set the output high. And then if we are reading one of the dip switches, a 1 would indicate that the switch is on because it's connected to VCC, and a 0 would indicate that the switch is off because it's connected to ground. Again, instead of reading from the pen, you can just set S equal to J244, and then S will be set equal to 1 or 0. Alternatively, you can use the read method. Okay. There's another method that actually disconnects the GPIO pin from the bus, forces it into a high impedance state. That's the high Z method. So that would be J244 high Z. To restore it to an active pin, active IO pin, we can use the drive method. Okay. Notice here there really isn't in the pin class a differentiation between input or output pin. If we read from it, it's going to be set to an input state. And if we write to it, it's actually set to an output state, and that's done automatically for us. So again, refer to this particular schematic, which is in the platform schematics folder. I pulled it up here earlier. It's a multi-page schematic, and I showed you, I think, page 2 to determine where the LEDs and switches are connected. Okay. The processor we're using also has a flexible interrupt system with 41 different interrupt sources. 7 different levels are supported, with level 1 being the lowest and level 7 being the highest. Level 7 is a non-maskable interrupt and is not typically used with micro COS applications. Priorities may be assigned at each interrupt level to prioritize interrupts at the same IRQ level. So pretty flexible system. Configuring interrupts is for the ColdFire similar to configuring interrupts for other microcontrollers, but the NetBurner API does provide a few helper functions. Again, this is covered in the interrupts application note. But to really use these effectively, you have to dig into the ColdFire reference manual, which again is a 1,200-page manual, but interrupts are covered in chapter 13. But there's 2 steps in general for working with interrupts. First, you have to configure the interrupt source, whether it's a timer or serial I/O or from an external pin, and then configure the interrupt controller. To configure the interrupt controller, you have to write an interrupt service routine that is, of course, run when the interrupt is triggered. You can use any of the micro COS routines that do not block in the interrupt service routine. So that restricts you to post routines. Probably a better way to say that is you can't use any of the micro COS routines that block in an interrupt service routine. NetBurner provides a macro, just interrupt, to simplify writing micro COS compatible interrupt service routines. This is a special macro that makes sure that after the interrupt occurs, a task switch can take place if necessary. You have to set up the interrupt vector, level, and priority. Again, NetBurner makes this easy using a particular function, a high-level function, to do all of that for you. Okay. There are also several timers that are available. There are 4 16-bit programmable interrupt timers that provide precise interrupts at regular intervals. The first one, the 0 timer, is actually used as the tick timer, so make sure you don't use that in any of your applications. It also has 4 32-bit DMA timers that provide input capture and compare capabilities. They can optionally signal events using interrupts or triggers. So I'm only going to discuss the DMA timers here, and I'll refer you to corresponding application notes for both of these. The DMA timer module can be used for input pulse measurement. Either the timers, the PIT, or the DMA can be used for pulse width modulation, but the DMA timers have better resolution. The DMA timers can be clocked from the system clock or actually from an externally provided clock. I'm only going to talk about clocking them from the system clock. But when driving it from the system clock, it can be programmed to have a timeout value of anywhere between 13 nanoseconds and 234,562 seconds, which is about 5 hours. Okay. The 4 DMA timers are denoted DTEM0 and DTEM3. All 4 of these are available. Remember, it's one of the PIT timers that's used for the tick timer. There are 6 configuration and control registers for each of the 4 timer modules. So again, it's not easy to configure these. I'll provide some example code from one of the application notes that shows you how to set all these up, or set one of them up. You will want to read that application note in detail for more advanced use. So there's a timer mode register that does most of the configuration. That's the one that allows you to select between the internal or external source and whether or not you want to divide the system clock by 1 or 16. That's an option, so you can get longer time intervals. When you divide it by 16. That register also controls timer reset and then enabling the timer. There's a timer extended mode register that can be used to enable a DMA request, and an event register that reports capture or reference events. And then a reference register is the one that contains a value that can be compared to the DMA counter. So that's the one that would actually we set that to a particular value, and when the DMA counter reaches that value, that reference value, an interrupt occurs. The timer capture register is a 32-bit register that latches the DMA counter when we're using it to capture events, to time events. And then the timer counter register is the actual up counter. You can read that without affecting the count, but any writes to it actually clears that counter register and then we restart it from 0. Okay, so I do provide a sample program here that's based on the application note. To get you started with a DMA timer, we'll use this in the exercise today, and then complete details on the DMA timers can be found in chapter 22 of the reference manual. Again, I probably wouldn't, I'd refer to the application note first before turning to the reference manual if you have any questions there. Okay, so I'll do another little short video here talking about today's exercise, but that concludes the lecture for today.